Hi guys, welcome back to another day of distance learning for chemistry. Yesterday we started looking at metals. Today we are going to finish off looking at the properties of metals. Just a brief recap from yesterday. Metals are made from the atoms generally on the left-hand side of the periodic table. And a metallic substance is made up of metal atoms in a 3D lattice shape. Let me make that bigger. So here's a 3D lattice. Someone asked you what a lattice looks like. It's just a three-dimensional shape in a regular arrangement. And the valence electrons, the ones on the outside, are free to move all around. So atoms are locked in place. Electrons are free to move, and we say they're delocalized because they're not stuck to just one atom. We looked at conductivity. The electrons are free to move, therefore it conducts electricity. Today we're going to look at malleability and ductility to start with. So these things are basically the same. Malleable means it can be shaped by force. So if you think of a blacksmith with a big hammer beating a piece of metal to shape, you can definitely do that quite well. And ductile means it's going to be drawn into wires, so pulled into a wire. And it's a similar sort of property to have. So are metals ductile? Yes, they are. Really good for making stuff out of, weird shapes, and great for drawing into wires. Now the reasons why they are ductile. So here I have my atoms in a 3D lattice shape. Here it's just a 2D shape to make it easier to look at. Now when we hit these atoms, imagine we're using a hammer, we'll smash them and they are just going to slide over each other. Now the important thing to say why it doesn't shatter is because the lattice does not shatter because the metallic bonds are non-directional and do not break when their cations are shifted. So these bonds are non-directional bonds. This is different to ionic substances, which we looked at right at the beginning of the lockdown, which when they slide over each other, the bonds are not directional, and that's going to force ions of the same charge to line up against each other and repel. In a metal like this one, the bonds are non-directional. And you can remember we said they are non-directional because imagine here is one atom. It's a positively charged ion because it's lost its electrons. It's not going to be just attracted to one atom or one electron next to it. It's going to be attracted to all of these electrons, which are all moving around all the time. So the bonds are non-directional. If the atoms are shifted, it's just going to bond with, it's just going to be attracted to another electron. So when the hammer is hit, atoms slide past each other and settle in a new position once the force is removed. And the important bit, does not shatter because metallic bonds are non-directional. We'll be looking more at that in a little while for the exam questions. I'll just hold on a moment. Next feature is hardness. This one you probably will not be asked in the test because it does vary a bit. So it says hardness of metals can vary. Titanium, very hard, while sodium on the right there, it's pretty soft. You can just cut it with a knife. In general, though, they're usually quite hard. Of course, there are exceptions. Mercury is a liquid, so that's not going to be very hard. And basically the reason why they're hard is because of their strong metallic bonds. And that's all it is to it. They have a strong attraction between the positive metal cations and the delocalized electrons. You probably aren't going to be asked this question about hardness though, so don't worry. Solubility is one that will definitely be asked, and it can be answered quite easily. So metals are not soluble in anything. It does say down the bottom, some metals may react with water. So if you throw a piece of a nail in some water, it's going to rust, and it'll eventually, that rust will dissolve. The rust may dissolve in water, but the actual metal itself doesn't. It's got to form rust first. So metals are not soluble in water. Here's a wishing well down the bottom. It's got heaps of coins in it. Definitely not dissolving. The reasons why: the attractive forces between the metal cations and the delocalized electrons, those are the metallic bonds, is stronger than the attractive force between the metal cations and the solvent, or the water. So that's all you've got to say. You're going to say, someone puts in a gold bar in a bath of warm water. Will it dissolve? Why not? And all you have to say is this: the metal will not dissolve because the metal cations have a stronger attraction to the delocalized electrons than their attraction with the water. That's all you got to say, and the proof of that is it's not dissolving. If the water was more attracted to the metal cations than the metal cations were attracted to the electrons, then it would dissolve. And one of the last ones, melting point, and this again is a general thing. Generally, metals have high melting points. You've got to heat them up lots and lots before they start melting. Of course, you're going to say, what about mercury, which is a liquid, and gallium, which has a very low melting point, you may know. They're just exceptions, so what we're going to do is ignore them, which is a very healthy way to do that. So what we're going to say is metals have high melting points. See, so here in bold. But why? So in order to melt a substance, sufficient energy must be added to the substance to break the attractive forces between particles. If they ever ask you a question about melting point or boiling point, that should be the first thing you should say. In order to melt a substance, or in order to evaporate a substance, heat must be added to break the attractive forces between the particles. And what are the particles in a metallic substance? I've said it a few times. They are cations or atoms. Okay, this is maybe going to get a little bit confusing. These here, well, they call them positive nuclei. Yeah, okay, so they call them numerous things depending on if it's in the psi pad or where. Here they call them positive nuclei, and their electrons are running are delocalized. The reason why I don't like that is because a nuclei is only the protons and the neutrons. And the thing is here, this nuclei, these atoms are going to be the protons and the neutrons and the electrons which aren't free to move, so the non-valence electrons. They're going to be the electrons in the energy in the electron shells before the valence shell. They're called positive nuclei. Personally, I just call them metal atoms, which is the easiest way to do it. Just call them metal atoms. They also sometimes call them cations as well because they've lost electrons, but I just call them metal atoms. So the attractions here are between the metal atoms and the delocalized electrons. And the important thing to know is that these attractions are strong. It says so there. So in this question, you're going to say the metallic bonds between atoms and delocalized electrons, cations, are very strong. Therefore, a lot of energy must be added. Because a lot of energy must be added, that's going to cause them to have a very high melting point. All right, that's that for my slides. Now, just to reiterate it, we're going to go over these slides, which are basically the same thing. Solubility. And you're going to explain, they're going to say, imagine the question is, does lead dissolve in water? Lead is a metallic solid. Lead is arranged as positive ions, so they're using the word positive ions or cations, that's fine, you can say atoms, held in place in ordered layers by strong attractive non-directional forces in a sea of delocalized electrons. Yeah. So saying the sea of electrons, you may see that in some books, I like to say sea of electrons, that's all these delocalized electrons. But as you can see in the first part, the student has said what sort of substance it is. The second part, they're talking about the bonding. They're talking about the structure. So the structure is positive ions held in place with a sea of electrons, and it talks about the type of bonding, strong, attractive, non-directional forces. So you've got the type of substance, the structure, and bonding. Substance, structure, bonding. These forces require a large amount of energy to break. Therefore, the electrostatic, you could just call those attraction forces of the water molecules, do not have sufficient strength to pull the atoms apart. Therefore, lead is insoluble, does not dissolve. It says up here, in order for substance to dissolve in water, the attraction between the particle and the substance must be less than the attraction towards water molecules. So in order for it to dissolve, the attraction between the cations and the delocalized electrons must be less than the attraction between the water and the actual cations. So there's a little model answer for one of those questions. Here, why isn't this going? Seems to be laser pointer, go away. Okay. Next one's got to do with malleability. So here we've got a nice suit of armor. It's probably been blacksmithed. And maybe the question would be, is iron malleable? First, say what it is. Iron is a metallic solid, just like the last one. Lead is a metallic solid. Lead is arranged as positive ions held in place. Iron is arranged in positive ions held in place in ordered layers. A lattice by strong attractive non-directional forces in a sea of delocalized electrons. Same thing. These forces require large amounts of energy to break apart the solid, therefore aluminium is not easily broken apart. Okay, you don't really need to say that. But the next bit's the most important bit. However, when pressure is applied, layers can slide over each other. Yep. And as the attractive forces are non-directional, the metallic particles remain strongly bonded. This gives the metallic solid the properties of being malleable and ductile. And usually these questions are going to be paired up with something like an ionic solid. They're going to say, which one of these is soluble, or which one of these is malleable? Explain why. This is how you explain it for the metal, and look at the ionic one later. Last one we're going to look at is melting point. So metallic solids have a high melting point, true. Why? Once again, say what sort of substance it is, metallic solid, then the bonding and structure. Then we say these forces require a large amount of energy to break apart, high temperature, therefore the melting point is very high. So if a substance has strong bonds between it, then a lot of energy is required and it has high melting point. So the strength of bonds between particles determines the energy required to break them, and therefore the amount of energy to change a solid into a liquid, melting point, where the bonds are somewhat broken. Metals in general have very strong bonds which make them solid at room temperature. Mercury is the exception. I'll look into that, why that is. I don't actually know why that is, but there's probably a scientific explanation out there somewhere. But yeah, the main thing to say metallic substances high melting points because of their strong attractive forces between particles. Last thing to show you before I give you some work is an exam question, because these are really interesting. This one is from 2017, and very standard sort of question you'll get is complete the table below by stating the type of solid, the type of particle, and the type of bonding between the particles in each solid. Now, one of these is metallic, one of these is molecular, and one of these is ionic. Now, I'm going to give you a moment to work out which one is metallic out of aluminium, magnesium chloride, or sulfur. Hopefully you all said aluminium. That is the answer. And the reason why you know that is because it is made from, well, because you've probably seen an aluminium can, or it's made from metal atoms on the left-hand side of the periodic table. Aluminium's just on the left-hand side of that divide though. Magnesium chloride is going to be ionic because it's made from one metal, the magnesium, and non-metals, the chlorine. And S8 sulfur is going to be molecular because it's only made from non-metals. Anyway, first I'm going to ask you the type of solid, metal, type of particle, and this is one which time and time again, even NCA change what they want you to say for this, but I'm going to tell you what I say for this is I call them atoms and delocalized electrons. All right, so here what they have for the actual answer is atoms, definitely the type of particles, or you can say cations and delocalized valence electrons, but just atoms and valence electrons is completely fine. And the attractive forces between the particles is going to be metallic bonds. Don't overcomplicate it, they're just called metallic bonds. All right, so circle the substance which has the lowest melting point. Aluminium, metal, high melting point, that's got a high melting point, and sulfur's got the low melting point, but we're just worried about explaining what, and then it says justify your choices, referring to all three of them. We'll just worry about the aluminium today, and what I would say is aluminium is a metallic substance made from a 3D lattice of metal atoms surrounded by a sea of delocalized electrons. Just very standard statement saying the bonding, the structure and bonding, also say strong, and these particles are held together by strong metallic forces, strong metallic bonds or strong electrostatic forces, you can call them. And then you say these bonds require a lot of energy to break, therefore they have high melting points. Have a look what they say. Well, this is even shorter. Aluminium is a metal with strong metallic bonds. These attractions require a lot of energy to overcome, so the melting point is higher than sulfur's melting point. Well, it's got a high melting point. These are model answers. They are good answers, and they are generally very, very concise, meaning they say exactly what you need to say and no more. If I was answering this question, I'd go into more detail myself, just to make sure I'm right. As long as you don't say anything stupid, you aren't going to lose any points for writing more. And the last question we have here is, have I gone past it? No, here it is. Click this, circle the substance which is malleable, aluminium, Y. Justify your choice by referring to the structure of your chosen substance for only aluminium. You don't need to explain why those ones are non-malleable. And what you'd say is that it is in the aluminium atom is once again in a 3D lattice of metal atoms with a sea of delocalized electrons which are held together by strong non-directional forces, and for this case non-directional is very important. So yeah, they go into a bit of detail here, which is nice. Aluminium is a metal made up of atoms in a sea of electrons. So here I've got atoms or cations. can use either. I reckon atoms is better. Why not use that? Which are held together by non-directional metallic bonds in a 3D lattice. The metallic bonds are non-directional as the bonding electrons are delocalized across the lattice, shared by many atoms. When a force is applied, the layers can move without disrupting these non-directional bonds. Thus, the structure can change shape without breaking the lattice. What a great answer. So yeah, I hope that explains why that happens and it kind of makes sense. Any questions you have, just let me know, drop me a line, try to explain it. But really, these are, these answers are really good, and of course they are on Google Class. If you go to exam questions, question answers, go look at them anytime, and they tell you exactly what you need for each achieve merit and excellence. So for merit, justifies choice with respect to structure and non-directional bonding for aluminium. You've got to say the structure about the layers and how they can move past each other and how it's non-directional. If you just mention one or the other, you'll get merit. And if you just say it's a lattice or you just say it's non-directional, you'll get achieved. So achieved's pretty easy. But you should all be going for excellence. Anyway, what I'm going to leave you with today is a couple of pages in the SciPad, which are, sorry, skip forward a bit. Ooh. Yep, 87, 88, and 89. 87, 88, 89. That's all I'm asking for today. I am going to leave it at that, and I will see you guys tomorrow. Goodbye.